My topic is application of XRD in structural transformation of cathode materials for lithium-ion batteries. This presentation consists of introduction, discussion, conclusion, and reference. This is introduction. For the past several years, lithium-ion batteries have been the most widely used energy storage method for consumer electronics. Two-dimensional layered oxide materials having the chemical formula lithium metal oxide, such as lithium cobalt oxide, lithium nickel manganese cobalt oxide, have been extensively utilized and studied as cathode materials for lithium-ion batteries for several decades. However, because of their limited energy density, these cathode materials fail to meet the necessary demands for lithium-ion batteries to power electric vehicles. As a result, lithium-rich oxide cathode materials have been developed to satisfy the energy needs for electric vehicles' batteries. These lithium-rich oxide compounds are two-component composites between Li2MnO3 and lithium metal oxide. Lithium-rich oxide are among the most appealing cathode materials and can deliver higher capacity compared to the conventional cathodes. Despite the high initial capacity of these lithium-rich oxide cathode materials, both capacity and voltage fade have been observed during subsequent electrochemical cycles. Structural transformation are considered as one of the major reasons for such voltage fading and first cycle irreversible capacity in these lithium-rich cathodes. So in-situ techniques to monitor the real-time structural transformations are emphasized in the study of lithium-rich system during electrochemical cycling. In-situ XRD is a proven technique for the study of structural changes in oxide cathode materials, including lithium-rich cathode materials. The uniqueness of in-situ XRD when applied to LIBs is the ability to monitor in real time the structural transformations, changes in lattice parameters, and phase composition during electrochemical charge-discharge experiment. This is a discussion. Powder XRD pattern and each R factor give a lot of information on the material structure. R factor R factor means the sum of the intensity of the 102 plane and the 006 plane divided by the intensity of 101 plane. First, our major peaks in the XRD pattern on the right were indexed by the R3M space group, and the two peaks marked as blue like this are indexed by the C2M space group. The later reflections indicate the presence of a second Li2MnO3 phase. Secondly, the clear splitting of 006 and 012 and 018 and 110 doublet confirm the material crystallized in the layered structure without formation of any spinel structure. The intensity ratio of 003 and 104 is over 1.2, which is also an indication of the layered structure formation. Finally, the R factor for this material is below 0.45, which demonstrates the hexagonal ordering in the crystal. You can see voltage profiles over time, intensity plots, and A and B C lattice parameters. In the first charging stage C1, for the first 1.5 cycles, the C parameters increases as evidenced by the displacement of the 003 peak. In this voltage region, lithium ions are extracted from the lithium layers since the energy required to remove the lithium ions from the lithium layers is less than the energy required to remove them from the transition metal layers. The extraction of lithium ions from the lithium layer eventually increases the electrostatic repulsion between the oxygen layers, which causes unicell expansion along the C axis. In the second charging stage C2, the C lattice increases smoothly and the A parameters remains constant, which suggests that within the plateau region, the average ionic radius of the transition metal ions remain the same. For this reason, the charge compensation must occur by another source, possibly during oxygen release. The third charging stage C3, the C parameter decreases, indicating that the lithium ions are being extracted from transition metal layers. In the first discharging stage D1, the C parameter increases, which indicates the expansion of the unicell along the C axis during lithium insertion into the transition metal layers. In the second discharging stage D2, the Z-axis decreases, which is in accordance with the change in the position of the 003 reflection. This indicates the filling of vacancies in the lithium layers by lithium ions, which decreases the electrostatic repulsion among oxygen layers. And for this reason, construction of unicell along Z-axis occurs. The 101, 102, 104, and 113 peaks after 36 cycles show similar behavior during charging discharging as compared to flashily assembled electrodes. However, interestingly, new peak at around 28.5 degrees appear after 16 cycles during low voltage discharge in the D2 stage. This peak remains during low voltage charging and then disappear when charging beyond that voltage. This reflection is the characteristic 440 peak of spinel phase, possibly due to the presence of LIMN204. The overall structure still remains layered, but it is expected smaller size spinel domains may have been created in the crystals and locally integrated into the layered framework. The presence of such spinel phase may alter the voltage profiles in 16 and 36 cycles. The discharge voltage plateau shifted toward the lower voltage profile, which is called as voltage fade. As I explained before, this voltage fade might be directly related to the formation of a spinel phase that was observed after 16 and 36 cycles. This is conclusion. The structural changes in Lithium-rich cathode material was observed in real time using in-situ XRD. Powder XRD patterns and SAED imaging give lots of information on the material structure. The cause of the oxygen release was investigated by observing A and C lattice parameters during the charging-discharging process. The layer to the spinel-like phase transformation is the major reason for the depression in the discharge plateau during electrochemical cycling. Thanks for listening.